Un, dos. Check. Un, dos. Sí. Sí. Un, dos. Uno, dos. Un, dos. Sí. Un, dos. Un, dos. Sí. Un, dos. Check.
Sure.
Uno, dos, tres, cuatro, cinco, seis, siete, ocho, nueve, uno, un, dos.
So you're going to see what's being streamed, or
We can hear you.
I know I try to talk very quiet while I fall asleep.
Sí, podríamos esperar algunos minutitos más, ¿no, Eve? ¿Te parece? 5. So the streaming is like... En el streaming hay algo... ¿Está pasando algo? ¿Está eso? ¿Ya?
Sí.
Ah, listo, perfecto. Sí, sí, sí. Maybe we wait for a few minutes, yeah, and then we start. Yeah, because I see some people is coming here.
La red tecnología tiene mucho mejor señal vieja.
¿Quién es el power?
Y para poder ver, yo, si hay preguntas, necesito conectarme. Y acá no, en el wifi que tenemos nosotros son pésimos. Entonces, todavía no sé por conectar. Me van a conectar con un cable.
¿En serio?
Ajá, y me tengo que sentar en el fondo.
Astronomical Society of the United States. So I think I could go on for a while, but I would rather thank Sami for being here, and we'll give the word to him so he can teach us something about, for the next hour, about the sun's magnetic field and its variability. So please, Sami, welcome.
Yeah. Good afternoon, ladies and gentlemen. It's a great pleasure to be here in Mendoza. I have known people from Mendoza for at least 20 years, met Ebe at that time. And it's been a long time, and I've heard many good things about it, especially the wine, of course. But I never had the chance to come here, so it's a great pleasure to be here finally and to meet many new people, meet old friends again. And it's a particular pleasure to be able to tell you something about our work on studying the sun. Before I do that, however, I would just like to introduce my institute in a couple of slides and say something about the research school, which Francisco also very kindly mentioned. So the Max Planck Institute for Solar System Research is one of the 86 institutes in the Max Planck Society. They're distributed all over Germany, some of them also outside, but mainly within Germany. They're named after Max Planck, who got the Nobel Prize in 1918 for the discovery or invention of quantum physics, if you want. And Max Planck wrote, "Insight must precede application." And so there are research entities in Germany which try to apply research. Germany is an industrial nation, so scientific application is very important, but the Max Planck Society mainly works to do the basic research, covering all the fields that any typical university would. Very strong in natural sciences, in life sciences, but also in social sciences and the humanities. They don't do everything in the Max Planck Society. Try to identify fields which are innovative, which are changing, which are challenging, or which require a long time to get results. And our field is one of those because we build space instrumentation that takes decades very often till you get results from there. And it has been extremely successful. It's one of, if you look at, for example, citations to papers, Max Planck is up there together with Harvard and Stanford, the top universities. It had 23 Nobel Prizes since its foundation in 1948, including 5 in the last 3 years. So it's really very much in the limelight. Now, our institute, like all Max Planck institutes, typically has more than one director. So we have departments, and each department has a director. So in our case, there are 3 scientific departments which cover the solar system, different parts of the solar system. So in my department, we study the sun and the heliosphere, basically studying the atmosphere of the sun and what's beyond. And then we have a planetary sciences department being led by Thorsten Kleine, and looking at the interiors of the sun and the stars using helio and astroseismology is Laurent Gison and his department. We have a fair number of ERC groups, that's the European Research Council. They give huge grants. These are multiple million euros, and they're very hard to get. Only a few % of applications get there. We have 8 ERC groups. That's more than many universities in Europe as a whole university. We have other research groups, etc., Marie Curie, so on and so forth. And we have the research school, but I have a separate slide on that. That's about typically 40 PhD students that we have at a time. There are altogether about 300 employees, of which a bit more than 100 have permanent positions, and about 150 or so, half of the total, is scientists. Then there is a fair amount of infrastructure, especially if you want to do space instrumentation. You need that. These are clean rooms, electronics facilities, test facilities, mechanical services, a big computing center, etc., etc. As I mentioned before, the methods we use, we build, we design, build, test, fly, operate instruments, mainly on spacecraft, but also on ground-based observatories, and also we have balloon missions. We do the observations and the data analysis, but we also do theory and simulations, so the whole spectrum of what you can do. The image here is taken from the European Space Agency, and they have like 3 or 4 of these posters. This is ESA's fleet in the solar system. There has one for astronomy, one for Earth observations, etc. This is for the solar system. So these are all the missions that ESA has been flying in the last decade or two, studying the solar system. And then I went and looked and said, okay, on which of these missions have we got instruments or have contributed to it? It's actually all of them. And in addition, many more which come from NASA or our ESA missions, which are not for solar system, but for example, for astronomy, etc. All in all, we have contributed to more than 50 instruments on space missions, on balloon-borne observatories and ground-based telescopes, which is a fair amount. Okay, finally, before I actually go into the talk, an introduction to the International Max Planck Research School for Solar System Science. Here we have a research-based or research-oriented program. It's very international. You can, in principle, do your PhD in 3 years if you have a master. It can take a little bit longer, but it's about that time. At our institute, together with the University of Göttingen or the University of Braunschweig, which is another town very close by, we try to give the students cutting-edge research projects. It's fully funded. There are excellent career prospects. So more than 2/3 of our alumni are still working in science. That that is quite good compared with the average of maybe like 10% or so for most PhD programs. We've had more than 220 PhDs, so it's not small number statistics in the meantime. There is a really good curriculum, which is entirely in English, so you don't have to worry about having to learn German or something. And life in Göttingen is very easy. It's a university city with lots of students, lots of research institutes, very international. And I'm very proud to say that we have had a number of Argentinian students, very successful students, of which 2 are here. Ebe was among the very first cohort, and Francisco joined us later on, and very happy to have him as a leader of a Max Planck partner group here. It's very easy to apply. You can just go to that website and apply there. The students are also very active. They have been organizing various conferences all on their own, inviting people. We give them some money for support, and they do everything themselves. And they call them rocks and stars for looking at stars and looking at the rocks in the solar system, so it works with the title. And this was one conference. And if you look carefully, Ebe was also there. I recognized her on the picture. Okay, so now let me start with the talk proper. This slide is aimed at astronomers, definitely not at solar physicists. And many an astronomer will tell you there are much more exciting objects in the universe, and the sun is actually quite a boring star. And if you look at this image of the sun taken with a small, 10-centimeter telescope in white light, it does not actually look terribly exciting, I have to admit. But let's zoom in, and at the same time, just let also the Earth grow so that you have roughly to scale, and zoom in into that little black patch, which turns out to be a sunspot. And while we're zooming, we change the telescope to a larger one where we can resolve structure on the sun better. And you see that the solar surface is really covered in all kinds of structure. You have these cell-like features around the sunspot. These are granules, these are convection cells bringing heat up in the bright inner part and cool gas flowing down in the dark network around it. And the sunspot itself also showed a lot of structure and a lot of dynamics. This is what you see in white light. If you look at the sun at different wavelengths, it will show you a totally different face. At the lower left, you see the solar surface has a temperature of around a bit less than 6,000 Kelvin. If you look at somewhat higher temperatures, around 10,000 Kelvin, you can see structures like in the lower left. Forgive me that the movies are not running very smooth. This may have to do with the internet connection. And the lower left, the movie was showing the chromosphere of the sun with the prominence of the solar limb. You only see a very small part of the solar disk there, mostly the solar atmosphere. You've got so-called spicules, which, if the movie were running, you would see waving back and forth like the tails of a happy dog. And then you have this prominence further up, which is also shaking and oscillating all the time. And the movie upper right, we see much hotter gas at around 1 million degrees. This is now the corona of the sun, the outer part of the solar atmosphere. You see hot loops of this hot gas, and one of the big open questions is, how actually is the corona heated? Now, the dynamics we have seen so far was sort of everyday. This is what you can see on the solar disk or observe anytime when it has any activity. But from time to time, the sun produces real fireworks, and that is seen in the movie running on the right now, where you see a flare, or you actually see these post-flare loops. Again, this is just 1 million degree hot gas. What happens in a flare is that, thanks to the magnetic field, a huge amount of energy is released, which heats the gas up to maybe 10 million degrees or so, but you don't see here, because you're only sensitive to the relatively cool gas of 1 million degrees. As the gas cools down, you start to see these loops, and the cooling happens very fast in the dense lower atmosphere. So you see the loops first at the lower heights, and then with time, it's a cooling front that you're seeing. It's not actually the loops which are rising, but it looks as if the loops are getting bigger, but you're seeing different loops with time. And the other major thing that happens is so-called coronal mass ejections. Oh, this movie is running very slow, which is a pity. It's a really beautiful movie, where a part of the sun's atmosphere is thrown out completely. These are billions of tons of material into the heliosphere. Sometimes it works and the material actually leaves the sun. Sometimes it doesn't, as in this case, and it falls down again into the solar atmosphere. And these coronal mass ejections, they can take material with them at speeds of hundreds to thousands of kilometers per second. And if one of them comes and hits the Earth, it definitely has effects on our natural environment, but also on our technical environment. But that's not something I want to go into very much here. Now, an important point is that basically all these active phenomena that I've shown here and many more are not just restricted to the sun. Almost all stars will show very similar phenomena. And actually, not just stars. You'll see the same things or very similar things happening in accretion disks, galactic cores, etc., etc. The difference is that on the sun, and although they may happen at much larger scales and be much more violent and energetic elsewhere, but we have the big advantage on the sun that we can resolve them. We can probe them in detail. We have enough light, it's close enough so that we can study the physics, which often happens at relatively small scales. And I'll show you an example of that later on. And so in a way, it is like a little bit like a Rosetta Stone for other astrophysical objects. Now, one thing that goes like a thread through a large part of solar physics is that all these active phenomena, as I said, everything I showed you so far plus much, much more, is driven more or less by a single quantity, which is the magnetic field. It's the magnetic field and its interaction with the turbulent convection in the sun's interior and atmosphere. And the difference, let's say, to the Earth, which also has a magnetic field, and the sun's magnetic field averaged is not many orders of magnitude stronger than the Earth's. It's maybe 1 order of magnitude, 2, but not more than that. But it looks a lot more violent, right? And there are multiple reasons for that. One of those you can see on the image on the left, it's complex. It's not a simple dipole. Yeah? It's highly structured. And actually, we're only seeing the very large-scale structures there. It's structured all the way down to the highest resolution, to the smallest scales we can resolve. Secondly, it's extremely dynamic. The field is changing all the time. And you see that in the movie, which is running now in the middle. Yellow and blue are actual measurements of the magnetic field at the surface of the sun, opposite polarities, and one field lines are coming out, the other they're going in. And these white lines, these curved lines, these loop-like structures, they show the connection between them. These are field lines, but they're not actually measured as field lines. What we are measuring is hot gas in the corona. And you can see that the hot gas is connecting the opposite polarities, so that this question of what heats the corona, why do we have a multi-million degree gas overlying a relatively cool atmosphere or surface of the sun of 5,000-6,000 degrees, obviously has got to do with the magnetic field. And the third reason that it's so important is that the atmosphere of the sun is totally charged. That means, whereas here, we are living in the Earth's magnetic field. The air flows through it, we walk through it, we don't know anything, we don't feel anything because we are in a neutral environment. On the sun, this doesn't happen. The gas and the magnetic field are locked, whether they like it or not. So if you move one, you will affect the other. Right? That makes the magnetic field so important. Okay, the little red square that I have now introduced onto this movie in the middle, that is sort of the size, just to give you a feeling of the whole field of view of this next movie here. And you see there where you had a very strong magnetic field. The magnetic field is the measurement is on the left. Now white is one polarity and black the other. On the right is the brightness, and you see that you have a dark structure there. You have a sunspot where you have a very strong magnetic field. So sunspots are obviously strongly magnetic structures. Before it was just a single patch. Now when we resolve it better, we see there is a lot of fine structure. In the center of the spot, we cannot resolve it, but surrounding it, we see these fibrillar structures, elongated fibrils of magnetic field extending from the inner dark part of the spot, but also outside the spot. You see a lot of small-scale structure around it where you have the individual small magnetic elements. Okay, so if we resolve better, we see more small-scale structure. Let's try and play that game again. Let's blow up a tiny little part where you have a little bit of field, but it's not very impressive in this image, and see what we get. Right? What's happening? Oh, yeah. Okay, so in this movie, again, on the left, the magnetic field. On the right, a brightness image. These, however, are not observations. These are simulations done with the Murray code. This is a radiation MHD code of the magnetic field and the gas in a box, small box compared to the sun, 6,000 kilometers inside compared to 1.5 million kilometers. So we have already decreased it by a few orders of magnitude. The color scale on the left implies blue, meaning very weak fields. These are maybe a few Gauss. To red, meaning strong fields, a few thousand Gauss. Okay? So you have an incredible filamentation of the magnetic field. Yeah. The average field in this box is something like 100 Gauss or so, maybe 200 Gauss. But you have orders of magnitude difference, and even if you start with a homogeneous field, through the interaction with the convection, these are convection cells we see on the right, you will get this filamentation within minutes, which is sort of the turnover time of the convective cells. The sizes of these structures are down to a few tens of kilometers, maybe a few kilometers. They have maybe not even been completely resolved in the simulations. Typically, what telescopes from the ground give you is a resolution of a few hundred kilometers, maybe 100 kilometers if you're doing really well in exceptional circumstances, a bit better than that. With DKIST, which is coming online now, we hope to do quite a bit better than that. In very small fields of view. The trouble is, you're always fighting the Earth's atmosphere. The Earth's atmosphere is turbulent, and it's going to mess up any images that you try to make. So the ideal thing is to get above the Earth's atmosphere. You can go to space, or if you don't have quite as much money for that, because you want to put a big telescope up there, you can put it on a stratospheric balloon. These are big balloons. You'll just see in a minute. So we designed this mission called Sunrise, which we have flown twice. Both of these times, or twice with scientific results at least, both of these times from Kiruna in northern Sweden, and it flies over the Atlantic and then is brought down again in northern Canada. This is because at a height of 35 to 40 kilometers in the summer, you have very steady winds. This is the stratosphere. Yeah? You're above the troposphere now. You have steady winds which go around the Earth in the opposite direction than we typically have winds in the troposphere. Right? Summer is a good time to fly because you're above the Arctic Circle, so you have sunlight 24 hours. You can observe the sun day and night, so to say. And the winds are stable. In principle, it takes about a week to get across to Canada. You could wait and get the whole thing to come back to Sweden. It will be about 2-3 weeks, except it doesn't quite work like that. Balloons go into Russia, but they don't come out. It has happened, and people have tried to call and say this is a scientific balloon, and the answer was, what balloon? We never saw a balloon. But it didn't reappear. Okay, I'll show you if this works. No, this was too far. Okay. Maybe I can go and run it. Yeah, okay. This is a movie of a launch, for the first launch that we had. So the balloon, it has got nearly a ton of helium in it. You can do lots of birthday parties with that. It looks rather small near the ground because it's held together and the helium is dense, but by the time it's in the stratosphere, it expands to 130 meters. Yeah, you can do a football World Cup game in there and have some space for stands as well. So the balloon goes all the way down to that red part in the middle. The red part, that's a parachute. There is a little bomb in between that explodes when you want to bring it down, and then the parachute opens. And the payload, which is about 2.5 tons, is hanging from that crane there. The whole thing from top to bottom is 300 meters. I don't know which building in Argentina. Also in Paris, the Eiffel Tower is 300 meters. Everyone knows the Eiffel Tower, right? The driver of that crane has to get exactly under it when he releases it. Otherwise, it's going to go penduled back and forth. And if it hits the crane, that's not going to be good because we have a telescope with which we want to get a coin. Sorry, I don't know what peso coin is about this size in 100 kilometers. You want to resolve it. And for that, the telescope needs to be very, very finely adjusted. It was a perfect launch. These guys are professionals. They know what they do. And then it rises for 2-3 hours till it reaches the nominal height, and then it drifts with the winds across the Atlantic till it is brought down. Okay. Results. I just show you one result of this flight. There have been, well over 100 publications coming out of the first 2 flights. But this is just one nice little result, which I think shows the power of studying the sun from above the low atmosphere of the Earth. At this height in the stratosphere, the sky is black. You're above 99% of the Earth's atmosphere. And any turbulence doesn't play a role anymore. So what you see here is a small part of the solar surface. On the right, we see an image of the corona. You're in an active region here. On the left is, in that little small square, is a magnetogram showing opposite polarities of magnetic field. So white means field lines coming out of the sun, black going into the sun, gray means you don't have much field there. Okay, this was taken with the Space Observatory, with the Solar Dynamics Observatory, HMI, very widely used instrument. And this is what you see. You can see there are these 2 opposite polarities and all that. This is what we saw with sunrise. You have an order of magnitude better resolution. You see it's still black and white as it was there before, but there's a lot more fine structure. And there was a big surprise, something we had not thought of before. You often don't think, you look, and then you see, right? Is that before, where it was just black, and there was white, and they were nicely separated, when we looked at the sunrise data at high resolution, we saw there were many places where black and white were very close together. That means you have magnetic field lines going this way, you have magnetic field lines going that way. It's also very dynamic. They're changing. We saw jets of material shooting out from these places. So obviously you have a lot of reconnection going on, where the magnetic field lines are actually connecting again together, releasing energy in the process. And so one idea that has come out of these observations is that in addition, so there have been many proposals for heating the corona and heating coronal loops. Why are the millions of degrees hot? Send up energy by waves, or you do something at the top of the loops, etc. And what we found, what could be happening, either as an important process or as an additional process, is that you have interactions going on at the foot points of these loops. You have new flux emerging, you have magnetic flux moving around, and then you get energy release at the foot point. You get hot gas shooting up into the loops and filling them with hot gas. At these points where the magnetic field changes its topology, you can turn part of the magnetic energy into heating the gas, and that's a good way to heat it up. The problem was, how do you get it up into the loops? But since we see these jets, it looks like it is happening. We still have to work out how common it is, but it is, in addition to field line braiding and waves, sort of the third big idea for heating the solar corona. Now, since the last successful flight of sunrise, which was in 2013, we did other things, and in recent years we have been working to improve the observatory. New instruments were built, a new gondola was built, more stable one, better image stabilization. You have to remember, you're hanging in the air, and you want to be so stable that you are down to hundredths of an arc second what the stability should be, right? Arc second is a very, very small angle, and a hundredth of an arc second is even smaller. So we are talking milli-arc seconds in a way. The new instruments, they have additional capabilities. They can study a much larger range of heights. So what you see on the left is the new version of the observatory. On the right is a cartoon of the sun's lower atmosphere. The surface is sort of that black stuff there, the horizontal part. Then you are in the photosphere, above that the chromosphere, the next layer of the atmosphere. It's very messy. That's because the sun is like that. It's a very turbulent medium with many things going on. You have shock waves, you have magnetic fields, you have interaction between the supersonic turbulent convection and the magnetic field, which then in turn has other effects, etc., etc. You have jets shooting out, so on and so forth. With Sunrise 1 and 2, we could only sample a very limited range of this height. And it's actually the range where things are more, how should I say, organized. It gets really messy further up in the chromosphere, which is maybe the least understood part of the sun's atmosphere. Why is he? Finally. Okay. And with Sunrise 3, we are hoping when we finally have a successful flight, hopefully in 2 years from now, that we will be able to see a much, much larger range of heights. At the same time, we will also be able to study the near UV part of the sun spectrum, which you cannot really do very well from the ground, and which so far has never been studied with really high resolution. And so one of the instruments which is going to do that, I think quite revolutionary, and Francisco here has played a really important role in building and testing this UV spectropolarimeter. So that's something we're looking forward to. Now, I've been talking about small scales so far. And I'm not going to leave the small scales, but I would like to just say something about larger scales, also time scales of the magnetic field and the activity of the sun. Many people have heard of the solar cycle. The sun's activity increases and decreases with time, and I'll come back to that later in the talk. The activity cycle of the sun changes everything. And you see that very nicely here in these X-ray images of the sun, one image taken every year, starting at a time when the sun was very active. That's in the front, and it's called maximum. And then as you go to the back, some years later, you have like 100 times less X-rays being emitted from the sun. And then if you wait a few more years, it's back to maximum and you get the X-rays again. And this is happening for as long as we can measure. Right? And the magnetic field is responsible for that as well. What we have not understood is how the cycle is actually produced. Right? We know that the magnetic field, or we think, that's what theory tells us, is produced by a dynamo acting somewhere in the interior of the sun. That is what most theoreticians agree on. That's where the agreement ends. Right? What kind of dynamo it is, where exactly, how it is being driven. People can fight for days, wonderful conferences, full of wonderful discussions to try and get that right. And so there is another mission, a new one, led by the European Space Agency, ESA, together with NASA, Solar Orbiter, which is to do many different things, including connecting the sun with the heliosphere, studying small scales, but it will also, in the course of time, produce important insights to the dynamo. And that is thanks to its very special orbit. So Solar Orbiter is this white curve that you see. Blue on the outside, that's the Earth. The brownish one in the middle is Venus, and there is Mercury. And you can see that Solar Orbiter goes on a very elliptical orbit, with perihelion being very close to the sun, about 1/4 of the way from Earth to the sun. Aphelion being relatively far away, which makes it extremely challenging, because when you're very close, gets really hot, so the front of the spacecraft is at around 500 degrees. When you're very far away, then the front of the spacecraft is at 50 degrees. Right? So you have optical instruments on there, which should work at the resolution, at the optical resolution they have. The other thing you will notice is that with time, this orbit tilts. It goes out of the ecliptic plane. So that solar orbiter will be the first mission. It's not yet there, but in a couple of years, which will start looking down with telescopes onto the poles of the sun. And the poles of the sun are a bit like the poles of the Earth were 150 years ago, terra incognita. You didn't know what is happening there because we are living in the equatorial plane of the sun. We can study the low latitudes in great details, but the poles are not really that well visible. And so that'll be very exciting. So we are leading the magnetograph that measures the magnetic field there. I'm the PI of that instrument, which we built in-house, but we also have co-PI ships of 3 other instruments, including the extreme ultraviolet imager. And so this is something like we think we will be able to see on the sun, at least for part of the time, where you're looking down on the poles. We know what is going on at low latitudes, but we have no idea. This is a simulation. You have no idea what the magnetic field at the poles will actually look like, how it will be structured. All the observations, or most of them, have terrible resolution when we're at the poles. Let me show you a couple of results. So since spring of this year, Solar Orbiter has been providing science quality data, and the extreme ultraviolet imager has the highest resolution ever images of the solar corona, and it is seeing small scale structures and events that were totally unresolved before. So it's got about a factor of 4 better resolution than the AIA imagers on the Solar Dynamics Observatory. And so on the right, you see the full field of view of the high resolution channel of the EUI, of this extreme ultraviolet imager. On the left is a blow-up, where you see one small brightening, small meaning like a couple of 100 kilometers in width and maybe 1,000 kilometers in length. These were called campfires. They were discovered by Solar Orbiter. Yeah, because it looks like a little flame, right, going back and forth. And by combining the observations from the EUI with, so this is in the EUV, in the corona, with magnetic field measurements taken by Phi. And you see 2 blow-ups on the right of 2 of these campfires. On the left, on the right, you see the magnetic field. And you can see how they connect 2 opposite magnetic fields. That is fine, that's all good. But it's interesting, and this is something we find for almost all of them, that one of the foot points has an opposite magnetic polarity very close by. So again, the same thing happening. At the foot points, you're having interaction between opposite polarity magnetic fields, which are then, we think, and that's also what models suggest, leads to the brightenings, to the heating up, dense, hot plasma in the corona, in this case on very small scales, as could not be seen before, and we think the same is also happening on larger scales. But let me show you another result, because one of the other models, this goes back to Gene Parker, 40 years, 50 years ago, who said you can heat coronal loops by braiding. That means you have field lines. Imagine, I'm living in Germany, so I know what a German magnetic field is. This is all field lines parallel to each other, right, going up like that. Now, if you start with such a magnetic field and you let it run, within a short time, you're going to get a magnetic field that looks more like the traffic in Buenos Aires at rush hour, right? So you're going to be going in all kinds of different directions, braided around each other, and so on. And what Gene Parker was proposing is that when you braid a magnetic field like that, you have 2 field lines which are crossing each other, trying to move in different directions. They're going to reconnect, they will lose some of their energy, heat the plasma, accelerate the gas, and you should have it. Very good. People have been looking for this braiding for decades since then, and they have not found it. There has been like one or two results based on a rocket experiment where they said, yeah, maybe we saw braiding, but those are very, very special cases. With EUI on Solar Orbiter, we have been seeing a lot more of these braiding events. So what it looks like is that there are many different ways of heating the corona, and they're all somehow acting. Which one is the dominant one? In which case, we will still have to see. But there are a lot of new discoveries coming just now. There is, end of the year is the deadline for submitting papers for the first special issue of Solar Orbiter results. I welcome you to have a look at that. There will be many interesting things there. Okay, so I am running a bit late, so let me hurry up a bit. This was so far about sun's activity and the magnetic field. Let me spend the rest of the time on the sun's variability. Variability means how does the brightness of the sun change with time? Does it change? And if it does, is it important or not? We know most stars are variable. And ever since people have been using things like the Kepler spacecraft to look for exoplanets, they found basically every star is variable. And the sun is no exception. It is variable, although not on a very large scale, which is good for us. Yeah? Would not be good if it were a very variable star. Is that important? Well, let's take a step back. The sun is the source of life on Earth. No sunlight, and at least the higher forms of life will be gone. The ones which are dear to our hearts, right? There are lots of microbes in the ground and at the bottom of the sea and so on. They will probably survive for quite some time. But humans, all the other beautiful animals, etc., trees, plants, doesn't look too good. And that's because sun provides us a lot of energy. 1.36 kilowatts per square meter. That's a lot, yeah, that you can cook your food with that. At least at the equator, at noon, if you have no clouds, if you average over the whole Earth, then it's less than a quarter of that, but still, it's quite a bit. If you look at it like that, in 20 to 30 minutes, the sun provides to the Earth enough energy to cover the yearly energy needs of all of humanity. Not bad. Of course, you don't want to go and cover the Earth for half an hour with solar panels and then take them off again, but you could get a fair amount of energy out of that. And I think that is certain, in a place like this, it definitely has a huge future. Now, there's another question that has been, sort of interesting me, is if the sun is variable, could that be having an effect on climate? Because 99.96% of all the energy entering the atmosphere from outside or from inside the Earth is coming from the sun. So if we change that, we're obviously changing the energetics of the atmosphere, which could change the temperature of the atmosphere, which is climate, basically, right? So, is it relevant or not? And why is the question important? You all know this curve. This is the global temperature over the last 160, 70 years. The zero line is arbitrarily set, I think, to 1940 or something like that. All the blue, each is the average of a year. All the blue curves, or all the blue bars, are years which were cooler than that average. The red bars, the years where it was hotter than that average. And you see, all the blue bars are on the left, the red bars are on the right. So there is a warming. It doesn't look huge, it's like 1 degree. Yeah. Today morning, it was way more than 1 degree cooler than it is outside. Summer and winter, the temperature difference is much larger than that. Equator poles, the temperature difference is much larger than that. But each of these bars is averaged over day and night, summer and winter, whole Earth's surface, and then a degree is a lot. Yeah? Now, you may not notice it in most cases, but there are some relatively sensitive natural systems that notice a degree quite a bit. These are glaciers. Yeah. And in my home country, Switzerland, we have a lot of these. You have some really beautiful ones also here in Argentina. These are two pictures taken from the same place of the Rhone Glacier, which in 1900 came all the way down in the valley. By 1960, you can only see the tip up on the mountain, and now you can see even less from that point. It has lost a huge part of its volume. Another example, this time from Alaska, the Muir and Ricks glaciers. In 1941, a sea of ice. In 2004, mainly just sea, with a bit of ice at the end. Yeah? So, they react. I have to give a word of warning. Glaciers have not just started retreating in the last 100 years. Yeah? They have been retreating ever since the end of the last ice age. It's a system which reacts over a long time. It reacts very sensitively, but since 1850, temperatures also increased for other reasons, for natural reasons, because the little ice age ended. And the glacier is still reacting to that. But they're definitely also reacting to the huge temperature increase we have been having. Oh. Now, that was to the question whether the Earth has warmed and why we should be interested in finding out the sources for that. Second question, is the sun variable? And it's actually not so easy to measure. People have been trying this for 100 years from the ground, and the results are basically crap, because changes in the, lost the word, transparency of the sky, even tiny changes are enough to destroy your measurements. You have to go into space. This was done for the first time in 1978 with a sensitive instrument, and this is the time series you get. The measurements are actually the colored bars there. The black curve is I think 6-month average over these, running average. You see very nicely the solar cycle in there. There are times when the sun is brighter, when it's less bright. The amplitude is small, 0.1%. Okay? The actual measurements look very noisy, but it's not the data, it's the sun. Here is a blow up of one of these dips. You see, it's always dips. It's not shooting up into the sky. It's usually going down. And here is a blow up of one of these dips. And at the same time, so such a dip typically lasts about 10 days or so. And at the same time, you have images of the sun taken at different times during the dip. And what do you see? At that time when the sun was darker, there were sunspots on it. Yeah, sounds okay. I have dark sunspots. They keep some of the light from getting out, and we understand why that happens. So the sun as a whole will be a little bit darker. Very good. If I now look not just at one dip, but take again such a 3-month average in this case, both for the brightness of the sun, the irradiance that's in blue at the top, and at the number of sunspots, which is in red at the bottom, what do we see here? The sun is actually brighter when there are more sunspots. So it's completely the opposite of what I've just told you. It makes no sense whatsoever. Yeah, put more dark sunspots on the surface and the sun gets brighter. Anybody have an idea what's going on? I didn't tell you the whole truth, okay? Sunspots are a magnetic feature. They are not the only magnetic feature. The magnetic field, besides the dark sunspots, also produces many bright features. These are smaller features. They're called faculae or plage. They are bright. Each of them is not so striking as a big fat sunspot, but there are many more of them. Many, many more. And so as you go from activity minimum to maximum, you have more dark sunspots, but you cover a much larger fraction of the solar surface with these little bright faculae. And they dominate. Now, the sunspots try to make it darker, and they do for a short time. They win, but over the longer time, the faculae win. And this is not just hand-waving. We can actually reproduce the observations really well. 95% of all the changes in the brightness of the sun can be reproduced based on magnetic field at the solar surface and how it makes some features dark and others bright. Let me see, the red curve is measurements, the orange is the daily, the red is a running mean, the light blue are what the model reproduces, and the dark blue is is the smooth of that. And the below is the difference between them. This model has one free parameter. In the meantime, we have a version where we don't we don't need the free parameter anymore. It still reproduces things nearly as well. So we think we have sort of understood what is causing brightness changes on time scales of hours to decades. Okay. To see if this could be important, the changes of the brightness of the sun, we need to look at longer time scales. We are talking here, climate has been changing on time scales of hundreds of years. This here is, to my knowledge, the longest running series of measurements in science. It's the record of sunspots. It starts here in 1610, which is not by chance, because in 1609 the telescope was invented. Before that, you had to do it with naked eye. You can, but the data are iffy. But since 1610, it's a relatively complete record. You see the solar cycle very well. There's just counting this, how many sunspots do I have on the sun? Right? And you see the solar cycle very well. You see that some cycles are very strong, others are very weak, and you see this period between about 1640 and 1700 or 1710, when there were almost no sunspots at all. This is called the Maunder minimum. And if by chance or not, it also happened to be the coldest, darkest part of the Little Ice Age. Certainly in Europe, it was a period of extreme cold. Frozen lakes, this is a picture by one of the Flemish masters, Hendrik Averkamp. I spent a winter in Holland and was looking forward to go ice skating on the frozen lakes. They did not freeze. It doesn't happen anymore. Yeah? In those days, it froze every winter for a long time. It was much colder. It didn't help that the 30-year war was going on at the same time. You didn't want to live in that time. There is another period around 1800 where the sunspot cycles are also not that strong. And this turns out to be a very cold decade as well. And actually 1813-14, that winter was the last time that the River Thames, which goes through London, froze to the extent that you could have a Christmas fair on it. They used to have that regularly, right? They had big tents and things and were selling stuff and so on. Doesn't happen anymore. But again, a word of warning, the River Thames today is not the River Thames of 1813. Because now they have dams and stuff, and the water flows in a different way. So you have to always be very careful with these things. Okay? Now we have a time series of 400 years, and we can be really proud that we have this time series. And still, we only have a couple of anomalies where we can actually go and check, right? Has the sun been behaving similarly or not? Obviously, what we need is a much longer time series. Difficult because we don't have any direct measurements. As I say, there are some Chinese records where you see where they did sunspots, but they're very scattered. In Europe, they did not see sunspots because they were not allowed to see sunspots, right? The church said Platonic theory is correct. That means the sun is perfect. So even if you saw something, it couldn't be. But nature is kind to us. It provides us a record of solar activity that goes much further back in time. And this record comes from cosmic rays. Cosmic rays, high energy particles coming from the depths of the universe, most of them from supernova remnants in the Milky Way, but very high energy ones even from extragalactic sources. When they reach the solar system, some of them get into the inner solar system. If one gets to the Earth's atmosphere, it will react with one of the molecules there. Usually it's nitrogen. Right? That's the most common, but it can also be oxygen, argon, whatever. They have sufficient energy. They're coming at near the speed of light. They have sufficient energy that you will get nuclear reactions as soon as you hit another nucleus of one of these atoms. And these nuclear reactions, they can be different types. There's spallation products. You see, it's very complex what can happen. But for example, if you have a proton hitting with high energy a nitrogen nucleus, it could turn in the reaction one of the protons into a neutron. So nitrogen has 7 protons, 7 neutrons, and now suddenly you have 6 protons, 8 neutrons, and instead of nitrogen 14, you have carbon 14. Carbon 14 is a radioactive nucleus. It has a half-life of around 5,700-800 years. So it's decaying slowly. If you see any carbon 14, you know it has to be produced by this reaction. If it's older material, if it's since the 1940s, it could also have been a nuclear weapon that also produces this stuff, right? But if you look at something that's older, carbon 14 was produced this way. No carbon 14 is left from when the Earth was formed, so there is no primordial stuff. That's why it is so good for people doing dating. Archaeologists love this, right? It's a very nice dating thing. Now, what happens with the carbon 14? I missed a step. It has to be stored somewhere. Now, the carbon combines with oxygen, forming CO2. Most of this goes into the ocean and is gone, but some of it is taken up by trees. So where instead of, trees don't care if it's C12 or if it's C14. They take it, they put it into their wood, and there it is. You can see how much carbon 14 was produced in a certain year by dating the wood itself. And the wood can be dated through dendrochronology by looking at the tree rings, how far or close they are, and you can do it with the precision of a year. Right? That is important. You need to know how much was produced at a certain time. Because if the production changes, that's going to, for the archaeologists, that'll be a disaster, right? If 2 times as much was produced, they will think, oh, this thing is much younger than it actually is, and the other way around. So they're very interested in getting this dating. Now you're wondering, okay, that's a nice story, but what does this have to do with solar activity? Okay. The production of carbon 14 is driven mainly by 2 things. What's coming from the outer universe doesn't change very much. Yeah, the sun takes 140 million years to go around the Milky Way. What's coming from outside is more or less constant. What does change is how much of what comes into the solar system reaches the Earth. That is affected by the strength of the sun's magnetic field. When the field is strong, it deflects more of these cosmic rays away from us. When the magnetic field of the sun is weak, more of them can get into us. So when the sun's magnetic field is strong, you get less carbon 14 being produced, and the other way around. The other thing is the Earth's magnetic field. That also plays a role, and it also changes on time scales of thousands of years or hundreds of years. So we have to take both of those into account. For the Earth's magnetic fields, there are other reconstructions. You can use that, you can remove that, and then what you're left with is the activity of the sun. now on a time scale of 7,000 years. In this particular case, we also have longer ones going back 10,000 years or so. Here we have reconstructed the number of sunspots, averaged over 10 years. We now have also higher resolution ones, but the diagram becomes a mess if you go with yearly resolution, right? But here you see that there were periods when the sun was very active, and the second half of the 20th century was one of these periods. These are marked in red. And there were periods when the sun was very inactive. And the Maunder minimum is the last of those blue ones when the sun was very inactive. So there have been multiple periods in the last 10,000 years or so when the sun had a so-called grand maximum or grand minimum. Why only 10,000 years? Well, carbon-14 has a half-life of 5,700, but that's not the real reason. The real reason you break off there is that before that you're in the Ice Age, in the real Ice Age. Yeah. And usually those trees don't grow anymore, and things are totally different at that time. So there are reconstructing solar activity would be difficult at that point. So as I said, second half of the 20th century was a grand maximum. Since then, solar activity has weakened again. We have left the grand maximum. We are now at a more normal type of activity in the last couple of cycles, and the present solar cycle looks like that also. This is how the sun has been for most of the time. We were a bit spoiled in the last century to have the sun so active. Okay. Once we can reconstruct solar activity over 10,000 years, we can also go and check if there were periods of time when the variations in solar activity or solar brightness were somehow following or leading changes in the Earth's climate. Here you run into the next problem. It's not so easy. There are no thermometers more than a couple of 100 years ago. So you again have to search for some kind of natural indicator of climate on Earth. This is not work we did. These were Earth scientists who did that, climatologists. And they looked at ice rafted degrees or changes in the oxygen 18 to oxygen 16 ratio in lake sediments or in stalagmites. And sometimes the data are more noisy, sometimes they aren't. But if you compare, there is a black curve and there is a red curve, and it makes no difference which is which. But they do show some agreement. So for these very different climate indicators, you have not perfect agreement, but it suggests that the sun may have, if you just look at it in a linear correlation kind of way, may have had an effect of up to 50% of climate change in the last 10,000 years. Now, remember, 10,000 years were very, very stable. This is the Holocene. This is after the end of of the Big Ice Age, right? Since the Younger Dryas. And so this period has been very stable. There still have been some variations in climate, and the sun seems to have had an effect there. Okay, so does this mean we can say, all right, we are not to blame, it's the sun for the change in climate of the last 100 years? Unfortunately, no. So here again, this is the last 140 years. Red curve, global temperature on Earth. There is a thin red one which is hardly visible here in the projection or even on my computer. Sorry about that. But this is not a plot I made. This was made by NASA scientists, and they used standard measures for the global temperature. The thick red curve is an 11-year mean. The yellow curve is our model that we made. They used that. We didn't do that. And for the last 20, 30 years, they used measurements. And you see that up to about 1980 or so, they may or may not, but they are sort of running in parallel a little bit, but since then they're totally diverging. Now, it wouldn't be science if people would not criticize, right, what has been done. And so there is some criticism about the measurements, because the measurements were carried out by different satellites, different instruments on different spacecraft, and intercalibration is always a mess. So it might be that it's not going down, but it's flat, maybe, but flat is still not increasing at the rate as you see there. So there is obviously a major divergence between what the sun could have done or is doing and what the climate is doing. And it's clear that even if the sun could have played an important role in driving climate in the last 10,000 years, it definitely is not doing it now. There are other things which are much, much stronger, and man-made greenhouse gases are the obvious candidate. Thank you very much for listening. Give her my greetings. Another famous person who went through the research school.
Okay, so Laura is asking the collaboration between the former MPIE and Argentina for the ground-based solar telescopes operating in San Juan was the initial connection point for many of the MPS alumni. Do you envision a similar collaboration in the future now that Francisco and Eve have started a group here in Mendoza? Okay, that was a very...
Right.
Yeah.
So yes, I do envision a collaboration, maybe not of the same type, but definitely a very close collaboration, which is also the reason I am here. Since a few years, it's 10 years or 12 years or so, the Max Planck Society has a program called partner groups, Max Planck partner groups, with which we can support in a limited way alumni, so people who have been at a Max Planck Institute either as a PhD student or as a postdoc, who go back to their home countries and make a career there, right? They don't just come back as a postdoc, but that they take the next step, and then we can support them to a certain extent, and that is what we did with Francisco, who has, been really one of the outstanding students we had in the school. And Francisco has then also been very heavily involved in the Sunrise project. So, yes, not providing a ground-based telescope for Argentina, but actually inviting Argentinians to take part in one of our telescopes going up into the air in this case. And it can also be space projects, certainly.
Great, thank you. Any other question? Eduardo?
This is, again, coming from my ignorance about how you deal with the plasma temperature. When you have these jets coming out, and you say they have like a 1 million degree temperature, is that taking into account the flow velocity of the jets?
Yes. Yeah. So the plasma temperatures are usually determined, what we usually have, there are different ways. But one way of measuring is from the light. So you look at which ions you see. So if you have 9 times ionized iron, for example, it needs a temperature of about 1 million degrees for it to be ionized to that level. If the temperature is much higher than 1 million degrees, then it will be ionized even more. So we will see some gas in the corona. We'll see a lot of gas at 9 times, 10 times ionized iron. In an eruption or a flare, we might even see gas of 18, 19 times ionized iron. That would be 8, 9 million degrees or whatever. So you can determine how much gas there is at different temperatures, how much gas means how bright your spectrum is, and from what ion it is, what kind of spectral line, you can also determine the temperature in a rough way. There are more clever diagnostics for doing that. People then also measure in situ. So Solar Orbiter, for example, or almost every solar mission, like Parker Solar Probe, they have in situ instruments which measure the gas directly, right? They will take up some gas, they will have mass spectrometers or whatever other instruments which can tell something about the composition, the energies, etc. And you can determine a kinetic temperature in that way, yes. And you can compare the two.
And they usually compare reasonably, I mean, just with this SACA type ionization temperature?
Yeah, partly. You know, by the time the gas has reached your spacecraft, which is far away, it has cooled down to a certain extent. So you don't usually get exactly the same high temperatures, but you do also see very energetic particles in flares and in the eruptions, which correspond to millions of degrees if you convert it into a temperature as well. The Parker Solar Probe is different because that goes very close to the sun, and so you start to see higher temperatures there than you would, let's say, if you're in Earth orbit.
Okay, we have another question over there.
With the sunrise, you showed that you can see with 1 and 2 some part, the hemisphere and a wider part. What is the limiting factor for how wide? I mean, you are looking at the whole hemisphere.
Yeah, so okay. I should be careful. I get carried away. So, yes, so you have instruments with which you see the whole sun. Your detectors and your telescopes and the imaging capabilities are your limitation there. The instrument with the highest resolution looking at the whole sun resolves something like 1,000 kilometers on the sun. With sunrise, we were trying to resolve 50 kilometers on the sun, so a factor of 20 better than that. It's a big telescope you need for that. Right? If I look at the whole sun and try to get all that light onto my detector, it will burn the detector, unless I have some way of shielding it. We have clever ways of shielding, but that is by picking out a very small part of the sun. So, yeah, I can say it in practical terms. So you have this big telescope, it focuses the light on one point. There the temperature gets really high. At that point, we put a metal wedge, which has a very good mirror on it. This is 45 degrees cut. The light comes here, and 99% of the light or more is just sent out into space, and the energy, right? There is a little hole in the middle, and only that part of the light of the sun goes through. And so we can only observe a small part of the sun. So there's a thermal reason, because otherwise it gets very tricky. And there is a detector reason. Right? I mean, you want to have a very fast readout to be able to be sure that no jitter and whatever, that your images don't get smeared. You have very big detectors in the meantime, but they're very slow. So they're not good for science like this. These are the limiting factors.
Okay, another question.
Is the high temperature that you said to him the only way to explain the ionization in the iron, as you said? And there
Yeah.
are ways to...
Yeah, there are people who have been proposing that you have very strange distribution functions of the particles. Right? Usually electrons are Maxwellian distributed. If you can somehow impart a totally different distribution on them, you could get a different temperature there. That is possible. These theories were proposed a couple of decades ago, they haven't really reached the mainstream, let's say. But it doesn't mean they're wrong, right? We don't know. And that's why I think also the Parker probe is really important. I promised you a movie of the flyby of solar orbiter of Earth. This happened in, almost exactly 1 year ago. And it flew by at a height of around 400 kilometers, which is very low. And that part of space is full of space debris, which is orbiting the Earth. But this thing was going at twice the speed of that because it was a flyby. Right? And just a week before, the Russians had destroyed one of their own spacecraft, and there were debris everywhere. And we were really worried, but it survived.
Nice. Okay. If there are no more questions, then we thank Sami again for joining us. Okay, thank you very much. I think we will now drink and some snacks while we also prepare some of our slides to tell Sami what we are doing.